Hello everyone. So we are back after a long time. Yeah, so in today's class we will discuss a lot of things, but those will not be in a lot of details. If you are interested, you can take separate courses because these are in-depth topics and which cannot be covered in such less time. So we will cover CNNs, RNNs and NLP. We will talk about the full forms of these. So CNN is convolutional neural network, RNN is uh, recurrent neural networks, and NLP is natural language processing. Okay. Yeah. So these are the three topics we'll cover. So introduction to convolutional neural network. We will also call it as CNNs. Before we understand what CNN is, you have to understand image processing or computer vision. Okay. So I'll just take one slide. Computer vision. So any image is generally made of pixels, right? So any image are made of pixels. These individual pixels have some color in it. It can comprise of if it is a black and white image, then it will have either white to black, that range from 0 to 256 or 255, right? So that range governs the intensity of one end or the other. So if it is close to 0, then it is white. If it is close to, sorry, on the other, it is other way. So if it is close to 0, it is black, and if it is close to 255, then it is white. Okay. So it is the other way. I'll just erase it. Zero to 255. If it is in this end, then it is black, and if it is this end, it is white. Okay. So this is actually the intensity of light coming out from that um, diode over there. And if it is a colored image, then each pixel have three different components, that is known as R, G and B. So these values can also be between 0 to 255, and it governs the intensity of that light. It is the red light, green light or blue light. Am I audible clearly? Because there is a fan blower actually in my end, and that
No,
makes.
no, no, not so clearly. That's what I was about to tell you.
Okay, just a minute.
Means your sound becomes intermittent for a few milliseconds or for a second.
Now is it all right? Is it better?
No, no. Means you just said, "Is it all right?" Then I thought you took a pause. Means no sound, and then is it better? I heard, "Is it better?" Like that.
Am I audible now?
Too much noise right now.
Too much noise. Just give me 2 minutes. Is it better now?
Yeah, a lot better.
Okay, thank you. So I'm saying is, so we were talking about computer vision. So each image are made of pixels, and each pixel can have three colors. If it is a colored image, red, blue, or green.
Shubham?
And yes,
Yeah. Okay, okay.
okay. So the red pixels can have intensity from 0 to 255. Similarly, green pixels can have an intensity of 0 to 255, and blue pixels can have intensity of 0 to 255. And this is how an image, so an image is comprised of these kind of pixels, right? So with any combination of these three pixels, you can get infinite number of colors. Okay. Now for computer vision, you see you have array of values, so you can convert an image into an array of values, right? So you can say that this is 0, 1, 2, 3, 4, so on and so forth. Suppose this is n, then this will be n plus 1, n plus 2. So you can create an array of values. This will comprise of the value coming from this cell, this will comprise of the value coming from this cell, and so on and so forth. So you can get an array of values, right? Now, so you can convert an image into array of values. And in the last class, we have talked about neural networks. So in neural networks, you have some input, there is some network inside, those are known as hidden layers, and you have output. So in the input, you can have, suppose there are 7,000. So these it will not be 7,000. Suppose it is a 255 by 255 pixel. So the lengthwise it is 255 pixel and breadthwise it is 255 pixel. So in total you will have 255 times 255 pixels, right? Or you can take a less resolution image. Suppose in the row you have 48 pixels and in the column you have 48 pixels. Then in the whole array you will have 48 times 48 pixels, right? So you will have so many number of values in that array. So now when you pass this to a neural network, you can imagine that the input of that neural network has 48 times 48, whatever it is. Let me calculate how much it is. 48 times 48, it is 2304. So 2304 number of nodes it will have in the input section or input. So you have input nodes, right? And this will be connected to the inner nodes inside the neural network, and this you can feed into a neural network and get an output. So it can be a classification image or it can be a labeling image. Suppose what this image comprise of, it is an image of a dog. So this neural network, when it takes this input, it can output something like dog with 98% probability, something like that. Okay, so this is how you can feed one image to a neural network to do some classification tasks or labeling task. Is that all right? Okay, so I assume it is all right. So if you go back and you will see that you can use this kind of neural networks to do handwriting recognition. So suppose you write two like this, someone writes two like this, someone write two like this, and so on and so forth. So what you can do is you can convert these in an image format, and you can uh, actually say what are the intensities of the each pixel when you write this kind of two. So suppose you're writing this two, so this will be something like this, right? And these pixels will be lighted up. There will be multiple pixels and each pixel will light up according to the whatever it is. So if it is a black pixel on white, so it will be have a value of higher white intensity will be here, and you can recognize using this. So you can feed this into a neural network and it will give you that it is a 2, and so on. So there is an MNIST database. I'll show you MNIST. It has multiple data sets of handwritten inputs, and this database has been used to obtain a algorithm, a neural network which can recognize handwritten so numbers from 0 to 9. Okay, so I'll show you. And these uses the idea of convolutional neural networks. You see, currently over here we are talking about, this is talking about how to feed a image into the input of a neural network. So you have an input, you have inner part, and then you have output, right? So you know how to feed an input image into a neural network. Okay, so first let me show you the MNIST database and then we'll talk about this neural networks and why it is known as convolution, and why what are the other things we do to preserve data and computational time. Okay, so I'll just show you in my computer. Just give me a second. I hope my screen is visible. Is my screen visible?
No.
Okay.
Yes, yes, yes.
This screen is visible, right? My computer screen?
Right now, yes, right now it is visible. Google search MNIS data sheet,
Yes.
data set.
Yes. So what is it? This is a very small data set which is showing, but it consists of a very large data set, so 60,000 training images, right? And what it contains multiple input for each of the values from 0 to 9. And that neural network is trained in this data set, and you can use it then to test and use it in your own. So you see, you can go to some website where the MNIST database has been used to train the model, and you can use this section to write your own words, and then it will tell you what it thinks it to be. So suppose I am writing 1, so it thinks it is 2 with highest probability, and some probability it says that it is 6. So maybe I have not written it very properly. This is an error. I wanted to write 1, but it thinks it to be 2. Okay, so I'll write 1. Maybe this time it seems, so it thinks it is 1, and with some probabilities also thinks it is 6. Okay, and so on and so forth. You can write 8, and you see it thinks it is 5. Okay, so you should, now it is 8, right? So this is how this MNIST database has been used. Just a minute. Okay, actually I'm using my mouse, so it is not very good. You can play with this. I'll share the link of this, and you can see that it works very good. I don't know why it is not working right now, but it works pretty well. Okay, play with this. And so this is on a built on this convolutional neural network. We'll talk about how this convolutional neural network works, and then we'll see. And I have prepared something, so we'll talk about this right now, but let me show you. This is actually a filter, so we will see what we are talking about over here, but let us see this short program, and then we'll move on to convolution. So this is actually a convolution. So what convolution does is, you have an image, and in that image it applies a filter. So whatever filter we use in our mobile phones, similar filters are being used. Like you can convert an image to black and white, or you can convert an image to just containing the edges of that image, and so on and so forth. Over here I have used a convolution. I'll talk about what this is. It converts the image and gets the edges of that image. Okay, so I'll just run this. You see, this was the original image, and it applied a filter on it, and then it obtained this. Over here you can see it obtained the edges of the image, and we'll talk about how it is obtaining this edges. How does it recognize that these are the edges of this image? We'll talk about that. Okay, so let us just move on to my iPad, and I'll talk about these things. Any doubt?
No, no. Okay.
All right. You see, when we were passing this image as one array, so when we are passing this image as one array, over here we are losing the relationship between pixels. We are just passing the values at individual pixel. But when a human sees an image, it does not focuses on individual pixel values. It sees the local structure of the image, the edges and all, and it relationship between different pixels, and then it makes a judgment that this image is of a dog or a cat or a boat, etc. Right? So this convolution tries to get this context into the neural networks. It tries to get the relationship between various pixels, such as edges, lower level details like edges and curves, and so on and so forth. You can also use it to get higher level details like some structures of like eyes, nose, and so on and so forth. Okay, so we'll see what a convolution is. Okay, so before that, introduction to convolutional neural network. Convolutional neural network are specialized neural networks designed to process structured data like images. So it is mainly used to process images. What are the key components? Convolution layer, we will talk about that. The example which I showed you was actually applying convolution to an image. It was applying a filter to detect some features. It may not only be edges. You can apply convolution to get other features as well. That was one feature, detection of edges. Okay, other features may be detection of red areas, detection of blue areas, or something like that. You can think about other filters as well. Pooling layer, it reduces the size of the dimension image. So you see currently, if this size of this image is very high, number of pixels in one side is very high, then the input to that neural network becomes huge. So this pooling, it actually shrinks the size of the image, it reduces the size of the image, and sends it to the neural networks. Okay, and then we'll see what is this fully connected layers, and we actually, it means that we are combining these two multiple times before passing it to the neural networks. We'll see. Okay, so what is convolution? So over here, this is the image. Suppose this is the image, or this is one section of the image. Okay, so suppose this is a1, a2, a3, or maybe like this I can write. Yeah, a1, a2, a3, b1, b2, b3. So suppose this value is around 20, this value is around 10, and so on. So we can give any value, right? So 100, 50, 30, 20, 150, 30, 20, right? So this is the value of the various pixels in an image. Now you see, what is this kernel? This is actually the filter which will apply and get an output. So it contains some values. It, suppose I give values like 2, 1, 2, 1. So what this will do is, we will put this kernel on top of this image. So over here we will put it over here, and what we'll do is we will get the uh, product sum. So what we'll do is we'll get 20 times 2 plus 10 times 1 plus, so this 2 times 20 plus 10 times 1 plus 20 times 2 plus 50 times 1, right? Whatever this value is, it will come over here. Then we will slide this to the next position. Where it will go? It will come over here. And again we will do 2 times 10, so 2 times 10 plus 100 times 1 plus whatever it is, and it will come over here. Now we will push it over here. Now this will be the new area where this kernel is, and then again we'll obtain this value, and at last, yes.
Is it supposed to perform matrix multiplication or normal multiplication?
It's not matrix multiplication, we are multiplying individual elements of the cell and then we are just summing it up. So 10 times 2 plus 100 times 1 plus 50 times 2 plus 30 times 1. It's just cell to cell multiplication, and it's actually a dot product.
Okay.
Right?
Okay.
And then we are shifting that kernel over here, and then we are getting this part and we are filling it over here. So what does it do? So you see, when the kernels have same values, suppose it is 20, 20, 20, 20. So suppose it is not like this, it is like this. 20, 20, 20, 20, and again these are also 20. So everything is 20, 20, 20, 20, and suppose this is 100, right? So what this will do, you see, when we apply this kernel, this value, and this value will be same, but this value will be little bit different, right? So it indicates some change in the image, in the local side of the image, right? It is indicating that suppose there is a sky and the values of the pixels are very close. It may not be exactly 20 for each of the pixels, but they will be very close for this area. But some obstruction is there, suppose some shadow or some tree branch is there, which changes the intensity of that pixel value, the intensity of the light in that pixel, right? So it indicates a change in pixel states. So this kernel helps identify features like curves and edges. And the kernel which I applied in the image which I showed you in the code is a special pixel which is actually used to detect edges. So it is actually a 3 by 3 kernel. I'll show you. I'll write that kernel for you. So that kernel is actually 3 by 3 kernel. It is like this, and each of the pixels, each of the cells have -1, and in the middle pixel and middle cell has a value of 8. Now what you do is, if you use this kind of pixels and suppose you have a cell of each 20, and there are other areas as well. So suppose you apply this kernel over here in this part of the image. Now what will happen is you will get 20 times -1, and this will be 8 times, right? Because this 1 2 3 4 5 6 7 8. So 20 times 1, 8 times, plus 8 times 20, because this is 8 and this is 20, it will become 0. So this kernel identifies region of same intensities. And if you have a region with higher intensity, suppose over here it is 100 100 100, and if you use that kernel for this block, then the value which you will obtain will be higher. So it indicates where the value of the pixels changes, and therefore it helps identify edges. Is that all right? This is known as edge detection kernel. It is a very special type of kernel.
Correct. Shubham,
Yes.
I have a question. In this particular scenario, image has a dimension of 3 by 3, correct?
We
For,
are
for,
saying that we
for,
have
for
taken.
instance, for instance, as shown in the figure, image has a dimension 3 by 3 and the kernel has a dimension of 2 by 2.
Okay.
Then the output dimension should be, if I'm not wrong, has to be 3 by 3 or not necessarily be.
No, no, no. So if you use this kernel, if you use this kernel in this image, you will get this output. Why? Because you have to shift the kernel. So initially, the kernel will be applied to this portion of the image. You
Correct.
shift the
One,
kernel,
two.
it will
Okay,
come
I
over.
got it. I got it. I got it.
Okay. So this is what convolution is. Okay. Now we'll understand pooling. So why are we doing convolution? We are doing convolution. So if you understand this in the context of this convolutional neural network, we are applying convolution because it helps us detect features. It might not be just the edges, it can have other features as well. All right, so it helps us. So for take the example of edge detection as well only. So edge detection helps us remove other unnecessary areas of the image. It gives you an input that only focuses on the edges of the image, right? So it helps detect features in the image. So that is what convolution helps us. Now pooling, so we have understood why pooling is used. Pooling is used to decrease the size of the image. Okay, so pooling reduces the size of the feature map. So feature map is actually an image, or it can be an image or whatever the output of the convolution step is. Okay, so that is a caveat. Retaining important information. So what pooling does is, suppose this is the input you are giving to this pooling algorithm. What it will do is, so suppose you are saying do 2 by 2 pooling. So it will take 2 by 2 areas of the image, and you can say what kind of pooling you want. So if you want max pooling, so in these 4 cells, whatever is the maximum value, it will retain that. So it will merge these 4 cells to be one cell. So suppose this was 10, this was suppose 100, this was 80, and this was 30. So the max pool will merge these 4 pixels and keep only one pixel, that is 100 maximum value. And over here we are not sliding, because we have merged these 4 pixels. We'll forget about these 4 pixels, we'll move on to the next 4 pixels. For these 4 pixels, again we apply max pool. Whatever the value is, it will come over here. For this also max pool, and for this also max pool. Therefore we will get a 2 cross 2 image. From 4 cross 4 image we have converted to 2 cross 2 image. Similarly, you can apply average pooling. So instead of taking the maximum value, you can take the average value. So it decreases the quality of the image in terms of visual perspective, but uh, from from the point of view of reducing, so it agreed that it is reducing the quality of the image, but you are also reducing the number of inputs the neural network is taking. So in that way there is some trade-off, but this trade-off is actually this for you have to see how much pooling you have to do. You cannot reduce the image, the quality of the image a lot. So there is a trade-off. You have to understand how much you have to use pooling, how many times, and so on and so forth. That you can understand when you're training the neural network. Okay. So this is how pooling works. Any questions?
No.
All right. So feature hierarchy in CNNs. So this we will talk about. So how this CNN works is, so suppose you have an image, you can do convolution. So you can do a convolution step, you can do a pooling step, and then pass it to a neural network. Or you can do it multiple times. So suppose you have a very large image, you can pass it to a convolution layer, you can pass it to a pooling layer, then again you can pass it to a convolution layer, again then you can pass it to a pooling layer, and then you can pass it to neural networks. So these decisions, how many times you have to do convolution, how many times you have to do pooling, depends upon when you are building the neural networks. You can also have multiple convolutions. So over here I have shown one convolution, but you can have multiple convolutions, one for only red pixels, one for only blue pixels, one for only green pixels, or maybe some other filter you are using. Over here this kernel may be different, right? So how do you want to decide what filter to use? That can also be fed into the training phase. So you don't have to decide what kernel you want to use, because some images can have different kinds of features which you will not be able to judge that this kernel will work best. So you have to give this decision to the training section only. So you have to say that while training there should be some decisions inside the model, that what convolution step to use, and then it will have, so those algorithms are inbuilt in the model. When you use some inbuilt libraries, it will have those kind of steps, those algorithms which will decide what kernel to use. And therefore there may have multiple convolution layers. It may not only have one convolution layer. And for each of the convolution layers, so suppose at this stage there are three convolution layers, right? So this is the first convolution layer, this is the second convolution layer, and this is the third convolution layer. So for each of the convolution layer you will have a pooling. Again, for so what you will do is, so suppose there are only one pooling and one convolution. So when you feed this to the neural network, you have to pass, so you have to flatten this and flatten this. So you will flatten the first red part, flatten the blue part, flatten the green part, and then you will pass it to the neural network. So you have to decide how. Yes,
Is it like concatenating?
yes, similar to that.
Okay.
Okay. So we have understood convolution, we have understood pooling. Okay. So lower layers, so when you have lower layers, it detects simple features like edges, textures. Middle layer combines features like shapes and patterns. Higher layer actually is systematic information like object categorization. So in the neural network you can have multiple hidden layers, right? So these layers, the first layers, initial few layers may detect the edges and textures. The middle layers may detect shapes and patterns, and last few layers might only focuses on the object categorization. So these shapes combined. So what can be some examples? So suppose the lower layer detects curves like this. The middle layer combines these shapes to circles, and the higher layer, uh, this captures more information. So okay, this circle seems like a balloon or something like that. Okay, so it is like that. Edge detection, shape recognition, and object classification. So these are the hierarchies in the convolutional neural networks. Application of convolution neural network: it is applied in computer vision, object detection, facial recognition, image classification. medical imaging, tumor detection, disease diagnosis, and yeah, it is also used in natural language processing, but little bit modified. We use actually RNNs because that works better for natural language processing. So I guess I shouldn't have included it over here. Okay. Any questions before we move on to the recurrent neural networks?
No.
Okay, thank you. So what is recurrent neural network? You see, when we are talking about these kind of CNNs, these are only focused on, so CNS is mostly used for images, right? So yeah, but what is recurrent neural network? You see, when you are passing information to this neural network, it is actually getting lost. So suppose these are the input layers. So this is not how input layer looks, by the way. It has multiple nodes, and these nodes are connected to inner nodes like this, and this may be connected to more hidden layers, and then it has some output layers. All right, so this is how neural networks may look like. So this is the input layer and this is the output layer. Now you see recurrent neural networks. So in convolutional neural network, you pass one input and you get one output, right? So the number of inputs nodes and the number of output nodes are a decision you have to make. So you can just say that the input node will have 100 or 1000 number of inputs, and the output layer can have 9 inputs. So for example, in the when we are talking about the MNIST uh, data set, it had 10 outputs. One output was for 0, another was 1, 2, 3 for till 9, right? So it has only 10 output nodes. It is fixed, you cannot change it. When you give an input, it can just say that it looks like 0 with 99% probability, it looks like 1 with 1% probability, and so on and so forth. So it will give you one output, only one output, like categorization. Or for example, it can say that this image seems like a dog. So in this image, it seems like there is a dog, or this image seems like for an orange, or something like that. So it will give you a fixed output. But when we are talking about languages, when we need output like languages, so for example, if you give one input as a bridge, and there is some shore, and there are people in the shore, and you pass this to a neural network, and you want output, for example, that there are people in the beach beside a bridge who are enjoying a summer. So if you want some kind of sentence where the length of the sentence is not fixed, and each word has context built in it, that there is relationship between one word with the other, you will not be able to use convolutional neural network to do this kind of task, because convolutional neural networks are better at categorization or maybe labeling. It labels the images or input it gets. It cannot output some sentence which has interrelationship between them. You see, they are talking about people, it is talking about bridges, it is talking about summer, and so on and so forth. So these are context, and these are interlinked between one another, which cannot be done using convolutional neural network. So for that we use recurrent neural networks. Any doubt?
No.
Okay, so I'll show you one example maybe. I have one, just a minute, I'll just share my screen over here. Okay, so this is one website I found, which image caption generator. So in that image, so this was the image I was using. I'll just show you the image again. So this was the image I was using. Sorry. So this was the image I was using. I uploaded it over here, and then I am saying write me a caption in a fun tone, and I'm saying convert image to caption. So when I click this button, it gives me some caption. Just wait a minute. I'll just refresh maybe. So okay, so you see it has given you two captions. The first is just a boat living its best life on waters. So this is not simple categorization task. It is talking about the context in the image, right? So this can only be done, I'll not say only be done, but these are majorly done using recurrent neural networks. Okay, so I'll just talk about recurrent neural networks. Any questions? All right. Okay, so recurrent neural networks are designed to handle sequential data by maintaining a memory of past input. So why it is saying a memory of past input, I'll come into that. Just the applications, language translation, time series prediction, speech recognition. So you can do language translation. You can give input which doesn't have a fixed length, right? Earlier we were saying that you have to input an image of size, so that when you translate it into an array, it should have a size of 1000. Now in recurrent neural networks, the input can also be of a variable length. Time series prediction, so for example you are predicting the price of a stock, or some other natural phenomena which has some kind of relationship between one time period to the other. Speech recognition can also be one application. Now, maintaining a memory of the past input, what does it mean? So you see, in a neural network, we have input, this is the network, and this is the output, right? But in recurrent neural network, we feed some data from the input, sorry, from the output of this network to itself in time. What does it mean? So suppose at time period t is equals to 1, we fed this. So suppose we are translating, or suppose we are giving this image of that bridge with a boat, that image which we passed to that website, right? So which we passed this image to the as input. Now what it is doing is, it is actually outputting one word. So for example, it is outputting there, and what we are doing is we are passing this there at the next time point is equals to 2, to the same network. This is network n1. Again I'm passing this there to this network is itself, and then it will output the next word is, and then I'll pass this is to the same network itself, a boat, something like that will come. So it will construct the output. So it has a memory of past input. This input, there is some memory of the past input, and it handles sequential data. So it can handle input data also, you can input in time periods. So suppose you are inputting some language translation. So you can input one word at a time and then output one word at a time. That is how recurrent neural network works. This recurrent means you're using the same network, but you're feeding some information from the earlier network to the next network. So you may not feed the output, you may feed some other features you are keeping from the network and then feeding it into the network back again. Okay, so this is how recurrent neural network works on a higher level. Is the understanding clear?
Isn't there the possibility of losing some of the features of the data when we pass the output of one box to the input of another box
So
layer? Sorry.
we have already outputted this word there in the output section, right?
Hmm.
And this input is already inside the neural network. So suppose we are talking about language translation. So what it will do is, it will suppose we are talking about C saw a cat, right? So first in that network it will pass C.
Why? Why? why the entire stream is not passed through the first layer? Because entire stream, let's say she saw a cat is a data, correct?
Right.
So it is supposed to pass entire she saw a cat as a data to the first block.
So suppose, first of all, what do we want to do with this? We want to translate it into Hindi. Okay. So it says she saw a cat and it wants to translate it into Hindi. Now, if you pass the whole thing to the recurrent neural network, you can obtain an output. It is not that you will not be able to obtain output, but as this input size grows large and large, you can pass a paragraph, you can pass a whole book, and so on and so forth. As the input size increases, the network will not be able to output accurately. That accuracy of the network will decrease drastically.
Yeah, yeah, accepted. But the reason behind asking this question is, if at single time we are passing in this particular instant a single word, correct? She
Ye- Yes,
followed by saw, followed by a, followed by cat.
yes.
Then why do we need to keep a memory of the past inputs?
So I'll tell you why. So suppose you are saying that why should we pass individual when we are passing individual networks. So what will happen is in Hindi, some words are not a direct translation of the English. So you can have the positions of the words may change in another language, right? In English you can say that noun comes before a verb and so on and so forth. In another language it may happen that it starts with a verb and then comes to a noun and so on and so forth. Or maybe in another language two words combined are written in a combined form, right?
Okay, okay,
two,
okay.
two combined words are written in one word in another language, or maybe one word is written in two words in another language. I am not able to give you some example right now, but I think you get what I'm saying,
Yeah, yeah. Means
right?
to have proper interpretation, it is necessary.
Yes.
To
Yes.
have proper interpretation of output data, it is necessary to have the memory.
Yes. Yes. So what it
Oh,
will do, it will take she first and then it may output. So currently we are talking about very vanilla form of recurrent neural networks. What it will do is first it will take she, it will not give some output, it will store it in this network and it will produce some features which it will pass to the next layer. Okay. So it will out, then it will input saw, and that this feature will come into this network, and then we will pass a, and then it will pass cat in a similar form. Once the network has absorbed all of these, see, saw, a cat, then it will start outputting. So at the last it will have this cat has been passed, so I'll just remove over here. So suppose seesaw has been passed, then a has been passed over here, and a has been passed and cat has been passed, right? When everything has been passed, then we will pass an end character to indicate that the sentence has ended. When we have passed this end character, then the neural network will start outputting. So then it will output the first word, whatever the word should be in that language. It may start with cat, maybe, I don't know. That depends upon the semantics and syntax of that language. It will pass the first word, then this word will be fed back to the network again. So suppose over here we are saying, I'll just erase it because I don't have space. So suppose this, we have passed the end word over here and this was the input portion. Now when we passed end, suppose the first output was, suppose wo, in Hindi maybe something like that, right? Or some other language, some word has been outputted. Now this word has to be fed to the network. It should know ki what word has been outputted, such that it can have a word, next word output, which has a connection with the first word, and then it will output again, and then this will be fed back to the network again. So there is some sequential data maintaining, and the output is then fed back to the network again. Is that all right? This is how it construct the output. Okay. So here I have written the formula. You will be able to understand this formula very easily. You see, xt is the input at time t. Xt is the input at time t, and this w is the weight, actually weight of the edge. So we have w times xt. What is u? Th plus 1. So H is actually the neural network's function. H is the function which converts input to output. So if we have a neural network, this is the input and this is the output, right? So H is that function we are talking about. So H t plus 1, whatever that feature we are getting from t plus 1 layer, we are feeding it back to this network by applying a transformation u. So u is just a weight, u times h t minus 1. And then there is a bias. Just forget about this bias. This is not important. So what will h t be? H t will become function of w x t plus u time h t minus 1. So the input at any layer is dependent upon the input at that time point plus an input from the layer or time above it, right? So this is how the new layer outputs, and whatever this output will be, it will fed back to this new layer and there will be some input, right? So this is how it constructs. Is that all right? And this bias term we have talked about when we were talking about this machine learning. Okay. Okay. So this is one example I have given prediction of stock prices, sequential data because stock prices changes every day. Recurrent neural networks predicts the next day's price based on the previous trends. Input is the historic price, output is the predicted price. Okay. I've just shown one example graph. It is just there for. Okay. So this completes recurrent neural networks at a higher level. I have just given you idea how neural network works, but this is actually a course in itself. So if you're interested, you can read more about this or maybe take some courses which are talking about deep learning. So these are part of deep learning. Okay. Now we'll move on to natural language processing, which uses recurrent neural networks. We have talked about recurrent neural networks in the context of, uh, you see, we are giving some input image and it is translating to some text. So you can input some text as well and output a text. So that is how we will talk about natural language processing. So you are processing the input language. So you can do it in multiple ways. We will talk about only how we are doing it using recurrent neural networks. Okay. So in past class, we have seen using Markov chain, hidden Markov chain, how to use hidden Markov chain for doing natural language processing. Today, we will see how we are using recurrent neural networks to do the natural language processing. Any doubt?
No, no.
Okay.
Please
So,
continue.
okay. So what we'll do is we'll take 5 minutes break and we'll meet at 6:53 and then we'll start. Okay. Thank you. So I hope you are back. Okay. So what we'll do is we will talk about natural language processing. So you see this this neural networks needs input in a form of array, right? So because the input layers has nodes and each node represents a value. Now for any sentence you can think about that sentence comprising of different words, and what we can do is we can suppose an example we can take that she enjoys music, and for each of the word we can put it into a vector. Okay, so in this we can say she is the first word and we'll call it as 1, enjoy is the second word, music is the third word, and suppose there was again a she, then we will have one more vector with 1 in the front. So each word is represented as a vector. This is known as one hot encoding. So we are encoding each of the words in a sentence in a vector format, and then this each vector could be fed in to each of the nodes in the input layer. What are the challenges? The challenges is inefficient for very large vocabularies. So you see, we are saying we will take one each word as a vector. You can have very large vocabularies, and in such that you will have to create large vectors and a lot of vectors. The number of vectors will be very large, and therefore it is inefficient. It cannot capture relationship or similarities between words. So for example, we are saying music and there is suppose another word called song, right? So we can have music and song. You see, music and song are related words. It is not as far as C and music. So C and music are more far away as compared to music and song, because song and music are similar words, and these similarities are not being captured by this vector format. So for example, we can take as male, female, he, she. So these words are very similar in nature, right? But these words, she and music, are very different words. So these relationships between words cannot be used. Or for example, similar words, same words. So for example, book and maybe textbook. So these are very similar words, but the relationship between these two words will not be captured by using this encoding. So one hot encoding is not a very good way to represent words in a sentence. Okay. There is another form of encoding or representation which is known as distributed encoding. Here what we do is, instead of only representing a word with at one position, inside the vector we give values at each of the positions. Now there can be these values can represent relationships. So what happen is, suppose we are saying she and we are having a word female. So these two words can have vectors with very similar values, because there are four values in these vectors. The four values in this vector can have very similar values, and therefore we can have some sense of similar words. That identity can be captured using this kind of representation. And you can see, if we have a vector like this, we can easily pass this vector to one of the input nodes and then we can use it, right? So I'll just read what I have written. Words are represented using dense vector, capturing their systematic meaning. Distributed relationships can identify patterns and relationships such as synonyms and analogies. Okay. So distributed word representations encode the meaning of the word into dense vectors of real numbers. Unlike one hot encoding, these embedding capture systematic relationship between words. So king and queen have similar embedding but different in specific dimensions. So king and queen, you see, this distributed encoding can be used to capture relationship between words. So for example, I have taken some, where is that example? Yeah, so this is the example. So when I say peacock and male, so suppose peacock, since these are vectors, you can represent it into in this space. Suppose peacock is over here and male is over here, right? These are actually vectors, so you can represent this into 4-dimensional or 5-dimensional or n-dimensional space. So suppose we are represented it into in 2 dimensions. So this peacock comes here, male comes here, and you take the difference between these two. So whatever the value of this vector is, you take the difference. And when you take the difference from female, and when you capture this difference, you will come to p hen. So you see, the difference between male and female is same as the difference between female and peacock and male is same as the difference between female and peahen. So these kind of relationships can be captured using distributive encoding. I have given some example. So what I am doing is, here is peacock, here is male. You take the difference between these two vectors and you add female. You just translate male to the position of female. You just move it over here. And when you come over here, you will see that in this position you have peahen, because these are vectors and these vectors have real values inside those vectors, and these kind of relationships can be captured using distributive encoding. Other examples can be doctor and hospital, and when you see what is the relationship between school, then you will see that doctors will be translated to teachers. Similarly, when you have cat and pet, that when you transform pet to wild, you can have some tiger or some other kind of uh, animal may come over here. Okay, so these kind of relationships can be captured using distributive encoding. Any doubt?
No.
Okay, so the word encoding are essential for tasks like language modeling, sentiment analysis, and translation. So what is word2vec? Word2vec is an algorithm for generating distributed encoding of words. So over here we have just talked about the encoding. This word2vec is an algorithm which transforms a word into a distributed representation of words. Okay, it uses neural network architecture to learn word embedding. The key architecture is skip-gram model. We will not talk about this model, but what is the objective? Predict the context of a target word based on the word itself. So whenever you have a word and you want to find its relationship with another word, you can get that relationship using this encoding. Okay. Skip-gram architecture, a neural network designed to predict surrounding context of a given word. So for the input layer, each word is encoded by a one hot vector. So it shouldn't be one hot vector. Okay, so for the input layer, it is one hot vector. For the hidden layer, just a minute, have I written it correctly? I'm not sure about this. I don't think it is written correctly. I will check this and post it in the WhatsApp or maybe Google Classroom. I'm not well read on this algorithm, skip gram architecture. I'll just read this and I'll inform you. Okay. Yeah. So we have talked about the different how can this distributed encoding capture the relationship between words. So whenever you have a sentence, the words in that sentence are related, and suppose you are translating an English sentence to a French sentence, you can check what is the relationship between first word and the second word, and you can then go to French language. You can write the first translation of the first word, and then you can see what is the relationship coming from the English language, and then you can translate the word from the English language to the French language using this kind of relationship. The one which is shown over here, peacock to male and peahen to female. These kind of relationships can be captured using these vectors. So these are some example encoding of these words: car, truck, road, etc. These are the example. This value can change depending upon what is the vocabulary you are giving to this word to vec algorithm, and it will generate these encodings for you, and we'll use this encoding, whatever we are obtaining for these words, as input to our neural networks. Okay. Limitation to one hot encoding, we have talked about the limitations. So one hot vectors are sparse and inefficient for large vocabularies. They do not capture relationship between words. So we have talked about this relationship, that there is no indication. Word2vec overcomes this limitation with dense and meaningful representation. Distributive encoding we have talked about. Words are represented as dense vectors in a low dimension space. These vectors capture systematic information. We have talked about this. Similarity between words can be computed using cosine similarities or Euclidean distance. So over here, when we were talking about this peacock male, female, and peahen, we were talking about Euclidean distance. That the distance between peacock and male is same as the distance between female and peahen. You can have another relationship as well. It may not be Euclidean distance. Euclidean distance, I guess you know what is Euclidean distance. It is, so for a two dimension, it is just the distance between, yeah, thank you. Okay. So application of word2vec algorithm. So it's systematic search improves search engines by matching query terms with systematic similar documents. Machine translation learns relationship between words in different languages. So you can translate from one language to the other. Sentiment analysis understand context and sentiment of the word in a given text. So what can happen is you can give a review and you can ask whether the review is positive or negative. Recommendation system suggest items based on systematic similarities. So you can also use this for building recommendation systems. Okay. Advantage: efficiently captures relationship and analogies between words, reduce dimensionality of word while retaining systematic meaning. How it is reducing dimensionality? You see, in one hot encoding, you require one at one position and all the other as zero. So if you have 100 words in a vocabulary, for each of the word you have to have one position. But in one hot encoding, sorry, in the other encoding, distributive representation, you can have a vector of smaller size and you can just vary the values of these vectors. And in that way, you can capture many more words in a very concise format because the size of the vectors will not change. You're just changing the values of individual elements in the vector. Okay. So it says handles large vocabulary with sparse data effectively because you're not building a very large dimensional vector. Now, what is attention? So you see, when you are inputting some words into a neural network and you are obtaining some output from the neural network, a recurrent neural network, you can say, whenever you are obtaining a word, it may not be related to each of the words in the input, right? So when you are doing translation of, so for example, from English language to French language, so suppose you are getting a word, that word may not be related to all of the input words. That sentence is created by different words and you're translating, suppose the first word is him and you want to translate him to some other language, suppose French. So that word may not be related to all the words in the input language. And what this attention does is it creates weights. It says when you are focusing on output of the first word, you focus on him more. So this is the probability or proportion of so this is how much you take him, importance of him. The other word, this is the importance of the second word, this is the importance of the third word, and so on and so forth. So it distributes the importance of each of the word in the input. So this is how attention works. It is an algorithm, it is a mechanism or algorithm which allows model to focus on relevant parts of the input data. You might not be interested in the whole input data when you are outputting one word at a time. You have to focus on some portion of the input data, and that is done by attention mechanism. Originally developed for sequence to sequence tasks like machine translation. So when you're doing machine translation, you might not be interested in the whole input, some portion of the one or two words together you may be interested on those two, and then you can write, right? Assign weights to the input tokens based on their relevance to the current output. Yes.
Is it like in a layman language feature extraction?
Sorry.
In a layman language, is it like a feature extraction? Because it
uh,
focuses on relevant parts, like features of that particular input.
no, it is not doing it. What it is doing is it is saying that suppose you have 10 inputs, 10 inputs you have, right? So I can just write like this. So it is saying when you are outputting the second word, this is the weight. So suppose I'll write the weight. So the weight of the first word is 100, the second word is 80, and third word is 30, then this is 20, this is 0 maybe, and this is 10, this is 8, this is 18. So these are the weights given to each of the nodes in the input layer. And when you do the sum, so when you say input 1 times 100 plus input 2 times 80, you obtain some transformation. Over here you see you're more focusing on this region of the text. So this is how
Okay.
attention you are having more attention in this portion of the text.
So that depends on the weights of that input nodes, correct?
Yes, whenever you are outputting one word in the from the neural network, you have to run attention, and then you have to obtain the weights of each of the input, and then for the second word also, the third word also, and so on and so forth. This attention mechanism helps you give accurate translation. Otherwise, the translation will be poor.
Okay.
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 So type of attention, there is soft attention. Weights are computed for all of the input tokens. So for example, in translating a sentence, all source word contribute to the target word, but but with varying weights. So this is how soft attention works. You can have varying weights for the input. What is hard attention? You select a single word token at each step. So for the output, you are saying I'll only focus on one word on the input. You have to select which word it is, but you'll only focus on that word. This will create poor translation. Self attention, it allows the model to consider the relationship between all the tokens in the sequence. So over here, the model gives the weights. In soft attention, you are giving the weight. But in self attention, it allows the model to consider the relationship between the words. And how are you obtaining the relationship? You're obtaining the relationship between using the ideas which we have talked earlier. Um, the data representation, when we're talking about, it has inbuilt in itself the relationship between different words. Okay, so it considers the relationship between all the tokens in the sequence. For example, understanding that it in the in this sentence, the word chased its tail refers to the dog. So this it in this word is actually talking about the dog. So these kind of relationships are understood using this attention. So when you are translating this sentence to any other language, say Hindi, so you will have to understand that this it is talking about dog, and some language may not use this it can just say some other way, and then it can translate, right? So this is how this understanding is built using self attention. I know I am talking about a lot of algorithms right now, but there are a lot of details for each of these. I am over here, I am just explaining the higher level understanding of each of the algorithms which will be used to do each of these tasks. So for self attention, this is how it will do. This is what it does. Sorry. Okay. Now transformers. So we will talk about transformers. Just give me a minute. So you see, when we are doing this kind of translation right now, we are saying that for the input, so suppose it has 7 words. So this is word 1, this is word 2, dot dot dot, word 7, right? For each of those, we will have the neural network take it. It will create some feature which will be fed back to the neural network, right? For each of that, it will be fed back to the neural network. And then when we have finished giving the input to the neural network, we pass an indicator, say end, to the neural network. And when this is passed to the neural network, then it starts outputting the first word. And then we'll pass this to the neural network again, and one, and then it will give the second word. This is how it creates. So you see there is a sequence. First it takes the input, and when it has compiled the whole input, then it starts giving the output, right? So this is actually, for a long time, this was the state of the art for machine translation. But this is very slow. Until and unless you have processed the whole input, you are not able to start giving output. and this was very slow. And that is where the idea of transformers came. It paralyzes the task. Over here we are saying that whenever we finish taking whole of the input, then only we'll start outputting. But in transformer, when in this type of neural networks, we don't wait for the whole input to get absorbed in the network. Okay, so this is a different kind of neural network. This is not the same which we were talking about earlier. Now what over here it does is, whenever you have a input, suppose word 1, with this word you can take it inside the neural network, and over here only you have to give the first output. Now when giving the this is actually not an output, it is an encoding representation. So in transformer we have two kinds of uh, um, steps, you can say. First is encoding and the second is decoding. So in encoding, the first word comes to the neural network, and we over here we get an encoded representation of the first word. Okay, I'll just write E1, and for the second word I will again put it into the neural network, and then I'll get an E2, new encoding. Now you see, you may argue with me that now when we are giving word 1 and word 2, the context of the words are lost. We don't know if this word, how this word is related to, so how word 2 is related to word 1. So what it does is, with this output it also takes one more argument, which is the position. What is the position of this word? So suppose position is first. For the second word, the position is 2. So it takes two inputs. This neural networks takes two input, the word itself and positional data, positional encoding. You can encode position in different ways. So you pass the word, you pass the position to this neural network and get an encoding. To improve this, okay, sorry. To improve this, you can also do self-attention. So what you are doing, I'll just write it in a better way. So first is the word 1 with the positional encoding P1. You pass it to the neural network. Before passing it to the neural network, you do self-attention. You do self-attention. What will this self-attention do? This will enhance the encoding which you are creating. Why? Because this encoding will know to focus on. So you might be at ith word, right? So you might be at ith word. So you have 1, 2, 3, 4, and you are at ith word. So this self-attention will tell you how much to focus on the first word, how much to focus on the third word, and so on and so forth. So you will do self-encoding, sorry, self-attention, and then you pass it to the neural network and then create an encoding, right? So EI. So when you have encoded the data, then you have to decode it to get the output. So how is the decoder looks like? The decoder is very similar to the encoder. In the decoder, you have an input character. What is this input character? So when you are decoding, you will create a sequence of outputs. So suppose the sequence is, there is a boat, there is a boat. This is the output. So the previous character, whichever you have outputted, will come first. This is the previous character in my output. So that is the previous word output plus positional encoding. So what was the position of this previous word? So over here it is, for this word there, it is the first word, positional encoding. Then you pass self-assessment because you have outputted some of the words, and what is the relationship between this word and this word can only be understood with self-attention. When you use self-attention, then you can pass it to the neural network and then you can get the output. So this is the output which you will pass into the next decoder. You pass this word, so that will come out to be is. Now you pass is, you give the position which is 2, do self encoding, pass it to the neural network and then obtain an output which will be A. Again you pass A, pass the position which is 3, do self encoding, sorry, self attention, pass it to the neural network, and then you will get the last word which is boat. And when you have obtained boat, then you will say pass end character. When you pass end character, then it will stop creating the output. Now you see, this is very simple neural network. What you can do is you can enhance this by doing self attention multiple times. You can do self attention 1 times, 2 times, 3 times, and then you can create more better outputs. So over here you will ask, where did this encoding go, because we have not used this encoding. So when we are doing the uh, self attention, at self attention we'll pass this encoding, because the self attention will also take input from the encoder which encoded the input. So I forgot to mention that this encoding will be passed to the self attention. This will take the data from the input and also the data from the previous word and then create the output. So this encoding will be sent to this portion. Is that all right? So this is the encoding portion and this is the decoding portion. Over here we have parallelized the task. Initially what we were doing is we are sequentially creating. We are giving the input first. When the input has ended, then only we were creating output. Over here you see it is being done simultaneously. You are giving a word, creating an encoding, saying what is the first word. If there is no first word, then start, and then you pass the encoding to the self assessment, and then you create the first word itself. Now you do this simultaneously. You will have encoding with you, you decode, and then you output. So encoding decoding works simultaneously when you are doing language translation using transformers. So this is how transformers works. A transformer are a neural network architecture designed for processing sequential data efficiently. They process all words in a sequence simultaneously instead of one at a time. This is parallel processing. What are the application? Language translation, text summarization. So you pass one big paragraph and you ask it to summarize to 2 lines. Question answering system. You can ask a question and it will give you an answer. Okay. Key components of a transformer: input embedding. It is actually how you are embedding the input. So the representation of the input. Each word is transformed into a numerical data. So how are we transforming into numerical data? We have talked about this. One hot encoding is there, distributive encoding is there. So we are inputting we are transforming the data such that it is numeric vectors. Then we are doing positional encoding. Adds positional information to each of the word. You see, we are passing what is the position of each of the words. Self attention determines how much focus each word should give to other words in the sequence. Multi-head attention, so we are saying, applies multiple self attention mechanism in capturing various concepts. So you cannot you can apply one time self attention, you can apply multiple self attention, and when you do that it is known as multi-head attention. And feed forward neural networks, it is actually input output, and this is the neural network, so it is known as feed forward. So you are giving the input from behind and you're getting the output in the forward direction, so that is why it is known as feed forward neural network. Process the transformed data after self attention. Encoding process, we have talked about this. Input, before I just read all this, is the idea clear how this transformer is working? If it is not clear, it is all right, because these are advanced topics of natural language processing. Transformers are advanced topics. We have moved away from recurrent neural networks to transformers. This was when we are talking about recurrent neural networks. Now we are talking about transformers. Okay. So encoding process, each word is a sequence. In the sequence is passed into the encoder simultaneously. What are the steps? Convert the word into embedding, add positional encoding to embedding, apply self-attention to understand relationships between the word, pass the transformed data through feed-forward networks. Output, encoded representation of the entire sequence. You see, we are getting an encoder. This encoder has the data of the word and its position. Okay. Decoding process, previous word output, whatever we have outputted previously, its positional encoding and encoded representation from the encoder. So we are also passing whatever we have obtained from the encoder. Steps, apply multiple attention step for understanding the context. Use attention on encoded representation from the encoder. Process through feed forward layers for generating the next output. This feed forward just means that we have an input layer, some hidden layer, and then output layer. So we are feeding it forward. That is why it is known as feed forward neural network. Output decoded sequence, one word at a time. Advantages of transformer, parallel processing enables faster computation compared to recurrent neural networks, effective for long sequences due to attention mechanism. So when you have long sentences, the context of the sentence is clear using this attention mechanism. High accuracy of tasks requiring context understanding. Scalability for large data sets and complex models. When you have large data sets, then this kind of uh, architecture helps in doing processing, because you can do take the input and output at the same time. Applications, language translation, so converting text between languages. Summarization, you can give one long document and then ask you to summarize. Sentiment analysis, analyze the text to determine if it is positive, negative, or neutral. Image captioning, so I just showed you some image and there was captioning, so it could have used transformer as well. That's why I said it may have used recurrent neural networks, or it could have used transformer. So generating text description for image. Speech recognition, converting spoken language into text. Comparison, for transformer, process all input simultaneously. You see why it's simultaneously? Because it is taking the input and obtaining the output. It is not waiting to take the input and then it will produce the output. Utilize self-attention to capture relationship, faster and more scalable. Recurrent neural network process inputs sequentially, depends on hidden states for context, slower for long sequences. Okay, so this is the end of this lecture as well as this course. Any doubt? Okay. All right. Thank you. I hope you enjoyed it. Yes.
Sure, sure.
Okay. So I was saying that I know I uh, couldn't cover this neural networks in details. Actually, what happened is I wanted to complete this course by the end of last year itself. Moreover, I did not see more enthusiasm from the students, so I also was losing interest in completing the course in more detail. That is the truth which I am telling you. Um, so yeah, so this is the end of this course. I hope apart from neural networks, you enjoyed the course, because I feel that I couldn't convey the concept of neural networks very properly. If you're interested, I can share with you some good resources for this topic, and then you can dive more deeper into these topics.
Yeah, please share.
Sure, I'll share it in the Google Classroom portal.
Yeah, Shubham.
Yes.
Yeah, I want to thank for delivering such a wonderful topic in a very crisp manner. No doubt the topics like neural networking and machine learning are deep, are of are vast in nature, but you really put forward those topics in front of us in an efficient way, rather I would say. So
Thank you.
it definitely will help us when we in future we learn those subjects in detail. But one request to extend the date of submission of assignments to the 26th February. You see, due to some busy schedules and some personal works, it really is not possible for us right now. It is not possible for us to go through the assignments. So please, if you can.
So if you are not able to submit the assignments, kindly submit the project because I have to report this
No,
to.
what's the deadline of the project submission?
It was last yesterday, 6th of
No,
January.
could you please extend it by
So okay.
uh,
So by the Acha,
19?
just a minute. Thank you for whatever you said. I really wanted this course to help people. Um, so if you really want to submit the project, please do so immediately because I have to submit the details of the students to ISSS because they will then start the next step.
What's the deadline? Because Shubham, as I told you last time, I have some medical emergencies at my home. So I again have to run down to my native place tomorrow and do some medical
Under-
formalities. So
So
in due course, if you can postpone, extend the project submission date, then that would do a lot favor to me, to
kindly
us.
you can tell me what is the date you are comfortable with for the submission of project.
19th.
19th of January. Okay, so please do so by 19th of January.
Sure.
Okay.
Okay. Thanks.
All right. Thank you. Professor Sudeep, any doubt or concern? Okay, so thank you. I hope you enjoyed it. I'll float one feedback form maybe. Take a minute to fill that form. I would appreciate it. Thank you for joining.
Thank you.
Hello?
Yes, yes,
Hello? Yeah,
yes.
yeah. Actually I could not focus today's class also. Sorry, extremely sorry. Last two classes and this class also I missed. I thought to join. I joined, but so many in between can come. Anyway, but really what Jairaj was saying that really it was very nice and very short within so short time, but you gave so many details of all these lectures. Thank you. Thanks a lot.
Thank you so much. So I would contact you in due time for some other purpose.
Yes,
So
yes, yes, yes.
thank.
These video lectures will be available in online mode, no?
Yes, yes, it is there
Shall
in
we
my.
be able to download?
I don't know. It is in Google, YouTube. If you know how to download YouTube videos, you can do that. I have no
It is
problem.
in YouTube,
Yes,
all the lectures.
yes. So
Okay, so
you can visit my YouTube channel anytime and you can see it. I'll not
okay,
remove.
then can you please share that link, YouTube?
I'll just show you. Just a minute. Just give me 1 minute. My website maybe. When you come here in the resources tab, this is the page for this course, and this is the YouTube playlist. So this is the playlist for all the lectures 1, 2,
Okay,
3,
okay, okay.
5, 6, 7, 8, and yeah, everything is there. I'll upload 13 as well,
Mm-hmm.
and it is here as well. You can come
Okay,
here,
okay, 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 okay.
and in the materials for the lectures are also here.
Oh,
Okay.
okay. Thank you. Actually, this week we have MBA visit. So in our institute, and for my specialization, VLSI specialization, the MBA visit is there. So last 2 weeks it was horrible, and now also in just one meeting it was going on parallelly, so could not focus anyway.
All right, no
Very
problem.
nice, very nice
I hope you
lectures.
enjoyed it. Yeah.
Shubham,
One student one day was asking about the project. What is the she was asking about the project, and I told I could not focus, and so I don't know exactly on the project. So how
I
they will be? Huh?
so what is the query? When is the submission deadline?
Submission deadline and say how to do the project. I told that exactly I don't know. So he said that if you get any information, please inform us. Okay.
So there's one Google Classroom I have created. Over there, I have given option to upload the files for the project.
Okay.
I'll just show that as well because yeah. So this is the classroom and this is the course. It is just
Hmm.
classroom.google.com. I have shared this
Hmm.
as well. So anybody can come here and upload the project over here. Yeah. So in this
What
project,
may be the topic?
so
Any
yes, I
topic
have
did you see?
shared. I have already shared. Just a minute.
Actually, as
Yeah, these are the topics I have mentioned. This on 28th November, I have mentioned everything in this post.
no, the thing is actually I did not think that I shall be able to do this project, so I did not focus much on this particular part. So when she asked, I could not give proper answer. So the topics are also there, and so she can upload, no, now also.
Yes, yes. Please
Okay.
do so. So I have given a deadline of 19th January. Please do so by then because I'll just send the details to them on 19th maybe.
Mhm. Okay. Okay.
Shubham, hello.
Yes, yes.
Yeah, one more thing to highlight. You, if I'm not wrong, are being from the mechanical background, correct?
I am from mechanical background. Yes.
Yeah, yeah. First of all, you really had great, great knowledge about all these electro-computer subjects like probabilities, neural networks, random processes, and all these things. So the course, from if I look from your perspective, the way you delivered was more than at par level. Excellent. Matlab, your understanding is far better than even an electronics and mechanical student. So so hats off to you for one thing. And another second thing, it's a little bit personal. You too, if I'm not wrong, uses a MacBook, correct?
Yes, yes.
And you being from a mechanical background, you might be aware of ANSYS software. Yeah,
Yes,
if I'm correct.
yes.
So could you please tell me, me to have a MacBook, I tried to install, means I did lot of search so that I can install ANSYS on the MacBook. So how could it be done? Could you please tell me?
Yeah, I cannot help you with that because I have not installed ANSYS in this computer. Actually, I have not
So
used it a
what
lot.
software do you use for 3D modeling?
I don't know because I left this area a lot while back, and at that time I was using Windows, so
Ah,
I'll
okay,
not be able to help you this with this.
okay, 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 okay.
And one comment on whatever you said. So, although I am from mechanical background, I have read about these concepts because I could understand these concepts because I am from a background of optimization. And whatever we have covered in this course are all originating from the roots of optimization.
Yeah, yeah, absolutely.
And this at IIT Kanpur, I was well taught these courses on optimization. I was not taught a course on artificial intelligence. I did not take a course on artificial intelligence, but whatever I gathered from the different courses which I took, it helped me build a base on the concepts of the courses which I am doing. So I'll just share one personal thing with you. So I generally float courses which I don't know a lot about. So this artificial intelligence was new to me, but I knew that most of the concepts which are used in artificial intelligence are known to me. I was learning simultaneously, I was delivering the course. So that is some truth I'll share with you.
Yeah, nice one, nice one. But thanks a lot.
Okay. So I'll end the course now. Sorry, meeting now. Thank you.
Thank you.
Thank you. Sir, since you are here, can we talk? I'll just end the
Yes,
record.
yes, yes. Yeah, sure. You can stop.